Good day to all of you. I am May Abrasaldo, the first reporter of the group. I will be the one to introduce to you our assigned topic or experiment, which is entitled Heat Transfer in a Double Pipe Exchanger. But first of all, let me bring into you my awesome groupmates, Misa Barquez, Mr. Amusin, Miss Ancheta, and Mr. Arong. This is the content outline of our report. The first one is the introduction, theory, and applications, which will be discussed by me, followed by the objectives and materials and equipment, procedure, experiment data and calculation, and conclusion, which will be discussed by my fellow reporters. Now, allow me to start with the introduction. The double pipe heat exchanger is one of the simplest types of heat exchangers. This is a concentric tube construction. It is called a double pipe exchanger because one fluid flows inside a pipe and the other fluid flows between that pipe and another pipe that surrounds the first. Perry in 1997 pointed out that the current U-shaped configuration addresses the need for a removable bundle configuration, as well as the necessity for the equipment to handle thermal expansion without the use of expansion joints, as these joints prove to be a weak point for the exchanger. He also noted that using double pipe heat exchanger or hairpin heat exchangers provide the ability to handle high tube side pressure at a relatively lower cost than the other heat exchangers. There are two flow configurations. The co-current is when the flow of the two streams is in the same direction, and counter-current is when the flow of the streams is in opposite directions. As conditions in the pipe change, inlet temperatures, flow rates, fluid properties, fluid composition, etc., the amount of heat transferred also changes. This transient behavior leads to change in process temperatures, which will lead to a point where the temperature distribution becomes steady. When heat is beginning to be transferred, this changes the temperature of the fluids. Until these temperatures reach a steady state, their behavior is dependent on time. In this double pipe heat exchanger, a hot process fluid flowing through the inner pipe transfers its heat to cooling water flowing in the outer pipe. The system is in steady state until conditions change, such as flow rate or inlet temperature. These changes in conditions cause the temperature distribution to change with time until a new steady state is reached. The new steady state will be observed once the inlet and outlet temperatures for the process and coolant fluid become stable. In reality, the temperature will never be completely stable, but with large enough changes in inlet temperatures or flow rates, a relative steady state can be experimentally observed. Let's move on to the theory. Heat can be transferred from one place to another by three methods: conduction in solids, convection of fluids, liquids or gases, radiation through anything that will allow radiation to pass even with lack of medium. Heat transfer occurs when there is a difference of temperature between two systems, and the transfer of heat is from that with higher temperature to lower. Conduction is the movement of heat through a substance by the collision of molecules. At the place where the two objects touch, the faster moving molecules of the warmer object collide with the slower moving molecules of the cooler object. As they collide, the faster molecules give up some of their energy to the slower molecules. Convection occurs when warmer areas of a liquid or gas rise to cooler areas in the liquid or gas. In liquids and gases, convection is usually the most efficient way to transfer heat. As this happens, cooler liquid or gas takes the place of the warmer areas where or which have risen higher. The equation for the heat transfer of heat by conduction may be written as Q over theta is equal to delta T over R, where Q is the heat transferred in time, theta, and the delta T is the temperature difference, and R is the thermal resistance. If the heat is being transferred through a homogeneous medium, the resistance is defined by Fourier's law as R is equal to L over Ka, where L is the distance across which delta T is measured, A is the area at right angles to the flow of heat, and K is the thermal conductivity of the medium. Both conduction and convection happen in heat pipe exchanger. The heat from the hotter fluid transfers heat to the pipe by convection. The heat travels through the thickness of the pipe through conduction, and the heat from the pipe to the cooler fluid through convection. If the heat is flowing through more than one medium in series, the total resistance is the sum of all the resistances, and the first equation become as shown in the equation 3, where delta T is the overall temperature drop. In the usual heat exchanger, heat is transferred from one fluid to another through a metal wall, and only the temperatures of the two fluids, but not the temperatures of the wall surfaces, are known. In this case, three resistances are involved: the resistance of the wall and the resistances of the two fluid films on the surface's wall. However, as the thicknesses of the films are seldom known, the quantities L and K are combined and a new term is defined by the equation 4. H is equal to K over L, where the H is the film coefficient of heat transfer. Then, the previous equation 3 becomes as shown in equation 5, where in the usual units, Q over theta is the heat transferred with the unit of BTU per hour, and delta T is the difference in temperature between one fluid and the other with the unit of Fahrenheit. K is the thermal conductivity of the metal wall with the unit of BTU feet per hour feet squared Fahrenheit. H sub 1 and H sub 2 is the inner and outer film coefficients respectively with the unit of BTU per hour feet squared of Fahrenheit. A sub 1, A sub m, and A sub 2 is the inner area, mean area, and the outer area of the metal wall respectively with the unit of feet squared. And as shown in the equation 6, where D sub 1 and D sub 2 are the inner and outer diameters of the pipe respectively with the unit of feet. Both conduction and convection require matter to transfer heat. Radiation is the method of heat transfer that does rely upon any contact between the heat source and the heated object. Radiation is a form of energy transport consisting of electromagnetic waves traveling at the speed of light. No mass is exchanged and no medium is required. This may occur in heat exchangers. The heat that is transferred from the outside pipe to the environment is expressed by the Stefan-Boltzmann law, which is shown in the equation 1, where QR is the net heat transferred with the unit of BTU per hour. P is the emissivity, 1.0 for a perfect black body. A is the area of the radiating or receiving surface. T sub 1 is the temperature of the hotter body, and T sub 2 is the temperature of the colder body. For the definition of terms, heat transfer by conduction is a transfer of heat through matter such as solids, liquids, or gases without bulk motion of the matter. Heat transfer by radiation is a process where heat waves are emitted that may be absorbed, reflected, or transmitted through a colder body. Overall coefficients is the overall heat transfer coefficient, or U value refers to how well heat is conducted through over a series of resistant mediums. Its units are watts over m squared degrees Celsius times BTU per hour feet squared Fahrenheit. Mean temperature difference. It is used to determine the temperature driving force for heat transfer in flow systems, most notably in heat exchangers. Also, it is a logarithmic average of the temperature difference between the hot and cold streams at each end of the exchanger. Film coefficients, also known as heat transfer coefficient, in thermodynamics and in mechanics, it is a proportionality constant between the heat flux and the thermodynamic driving force for the flow of heat, such as the temperature difference or the delta T. And lastly, the heat loss from bare and lagged surfaces. When a pipe bare or lag is used to carry saturated steam under pressure, heat will be lost to the surroundings because of temperature gradient existing between the steam and the surroundings. There are a few of industrial applications for the heat transfer in a double pipe exchanger. The first one is the double pipe heat exchanger utilizes true counterflow, to which maximizes the temperature differences between the shell side and the tube side fluids, resulting in less surface area required for a given duty. Double pipe exchangers are specially suitable for extreme temperature crossing, high pressure, high temperature, and low to moderate surface area requirements. So when your process calls for a temperature cross, when the hot fluid outlet temperature is below the cold fluid outlet temperature, a hairpin heat exchanger is the most efficient design and will result in fewer sections and less surface area. Double pipe heat exchangers use a single pipe within a pipe design and more commonly used for high fouling surfaces such slurries where abrasive materials are present, and for smaller duties, standard shell diameter typically ranges from 2 to 6. In commercial aircraft, heat exchangers are used to take the heat from the engine's oil system to heat cold fuel. This improves fuel efficiency as well as reduces the possibility of water entrapped in the fuel freezing in components. And lastly, the classic example of a heat exchanger is found in an internal combustion engine in which a circulating fluid known as engine coolant flows through a radiator coils and air blows past the coils, which cools the coolant and heats the incoming air. So many stores employ double pipe heat exchangers because of its inexpensive design and maintenance costs, versatility, and ease of installation. They are primarily utilized for sensible heating or cooling of processed fluids in applications which tiny heat transfer zones of up to 50 meter squared size.
Good day everyone, this is Judil Amusin and I am tasked to discuss on the objectives as well as the materials and equipments that are used in this experiment. So before all that, allow me to excuse myself because I'm not really feeling well when recording this, so you might hear my voice a little bit weird. I currently have cough and cold, so excuse me please. So going on to the objectives, the first objective is to apply the concepts learned in momentum transfer in a laboratory setup. So this is somewhat a refresher on the heat transfer concept, and this will enable us to check our understanding and enable us to visualize the theory on double pipe heat exchanger on this setup. So next is that we'd be able to calculate and obtain values of log mean temperature difference, that's the LMTD, the effectiveness and also the overall coefficient of the heat exchanger. Third is that we'd be able to apply the concepts learned in the given practice problems to further our understanding on the topic. So the same as the previous group, we also have prepared 2 practice problems for us to be able to check our understanding and try to solve similar problems that could enable us to deepen our knowledge on the topic. Going over to our next slide, we also have our materials and equipments. So for this experiment, we'd be needing a concentric pipe heat exchanger. I did not place an actual picture of a heat exchanger because it's very difficult to look for one, so I just decided to put the symbol instead. So yep, that's the symbol for heat exchanger. I know you're all well aware of that, since most of you are already on equipment design. So next are the thermometers, which will be used to measure the temperatures in the inlet and outlet of the heat exchanger. Next is a platform balance for measuring the weight or the mass of the water going in and out. Next is the weighing pails, the stopwatch for timing the intervals, and of course the water, which will be the medium for heat transfer. So going over our next reporter, please take the floor.
Good day everyone, I'm Kelly Ancheta. So the procedure of experiment heat transfer in a double pipe exchanger. First, the length of heating section was measured and the area of the heating surface was calculated. Second is the method of operation and its assembly were studied and the valves for countercurrent flow was set. Third is, after conditions of flow and temperature become constant, readings of time, inlet and exit temperatures of the steam and cold water streams, water meter readings, and weight of discharge at 2-minute intervals were recorded. Lastly is the experiment was repeated using different rate of flows which each run lasted for approximately 20 minutes. Then, the whole experiment was repeated using the parallel flow.
So this is a counterflow and parallel flow heat exchanger, and these are the various valves which are controlling the flow of water. Okay, so if both the directions of water are the same, then it's called as parallel flow. If the hot fluid flows in this direction and the cold water flows in that direction, it's called as counterflow. So basically first you have to switch on, yeah. Then you will get a reading here. Then you have to switch on the heater. And no, before that you have to open the valve for water. We will on the heater. So this is what is coming. The water comes in, and a part of the water will go as the cooling water, and the other part will be going into the heater. Then from the heated water flows through the inlet of the pipe. For parallel flow, we have to open this, close this. So for parallel flow means the hot water is coming this way. So the cold water should also come this way.
Okay.
So here's the end, cold water entry. So it should be going from there and coming here, not from here.
So close this one.
So we have to close this. We have to open this. This is the outlet from here.
Then just open it.
We have to come here and we have to open it.
Okay.
Open. This we have to close.
This one.
So now it is a parallel flow.
Okay.
Okay. Then we have to what we have to wait. We have to wait for some time until the water gets heated.
Okay.
Okay. Then it gets heated to a constant temperature.
Okay.
It should form a constant temperature. Actually T1, right? T1 is the inlet temperature of hot water. T2 is the inlet temperature, outlet temperature of hot water. T3 is the inlet temperature of cold water, outlet temperature of cold water. Okay. So let that be over. Then for counterflow. For counterflow, what you have to do is you have to open this,
Okay.
so that the water will come from here and go through that. Up to this it will come. Then it has to go through this way.
This way.
So we
So
have to close this
open-
and open,
open
that.
it,
Or
okay.
first open that one.
In this manner, right?
Okay, open, and this is closed.
Okay.
Then again you have to wait till this becomes steady, and then you have to take the calculations. We have to just take the readings,
That's
all the temperature.
That's only what we need.
Then you can get the effectiveness, and we can find the overall heat transfer coefficient.
So
For
we have-
flow rate,
so
so
we
what
have
you have
to
to do is you have to take a jug,
Okay. This one.
1 liter jug, and take the time for hot water. This is hot water.
Okay.
So time taken for 1 liter of hot water. Then we have to take the cold water. Then we have to change the flow rate. നമുക്ക് പിന്നെ പുതിയ സെറ്റ് ഓഫ് റീഡിങ്സ് കിട്ടും, അത് എടുക്കാം. അങ്ങനെ 3 സെറ്റ് ഓഫ് റീഡിങ്സ് എടുത്തിട്ട് കാൽക്കുലേഷൻ.
Okay.
So good morning everyone, my name is Mateo Ayaro and I'm here to present the data calculations and problem number 1 of the experiment. So let's proceed. So first is the data presentation on the counterflow and parallel heat exchanger. So first is the counterflow heat exchanger. So based on the given data, the average temperature of the cold inlet and outlet water are 92 and 158.63 degrees Fahrenheit respectively. The steam gauge reading is 27.18 psi and the inlet and outlet temperature of the steam is 198.54 and 165.92 degrees Fahrenheit respectively. So next is the data on the parallel heat exchanger. So based on the given data, the average temperature of the cold inlet and outlet water are 91 and 129.73 degrees Fahrenheit respectively. The steam gauge reading is 25.18 psi and the inlet and outlet temperature of the steam is 247.36 and 143.86 degrees Fahrenheit respectively. Then the length of the heat section is 11.5 feet, outside diameter of heating tube is 0.875 inches, and the inside diameter of the heating tube is 0.745 inches. Then we are going to proceed through the calculations. So first is finding the area of the heating tube, which is calculated using 2 pi times the diameter over 2 times the length, as shown in the slide. And the calculated area of the pipe are 0.2447 meters squared using the inside diameter and 0.20838 meters squared using the outside diameter. So the next slide we will continue by calculating the counterflow heat exchanger values. So first is the absolute pressure of the steam, which is done by adding the gauge pressure of the steam and the atmospheric pressure, which is equal to 41.876 psi, which is shown in the slide. Then we are going to find the inlet and outlet internal energy by using the steam table. As shown in the slide, the values of the internal energy is 387.76 kilojoules per kilogram for the inlet energy and 311.661 kilojoules per kilogram for the outlet energy, which is based on the absolute pressure of the steam and the inlet and outlet temperatures of the steam. Then we are going to calculate the heat loss of the steam by subtracting the inlet energy and the outlet energy, which is equal to 76.075 kilojoules per kilogram. Then, now we are going to calculate the overall heat transfer coefficient. By doing this, we first need to calculate the log mean temperature difference. The formula is shown in the slide, in which THI means the temperature of the inlet steam, THO is the temperature of the outlet steam, TCI is the temperature of the entering cold water, and TCO is the temperature of the exiting cold water. The calculated log mean temperature difference is 30.66 Kelvin, which is shown in the slide. The values of the temperature must be converted to Kelvin in order to find the temperature difference. Then after getting the temperature difference, we are going to solve for the overall heat transfer coefficient, which is equal to the heat loss of the steam over the area using the outside diameter times the log mean temperature difference. And the calculated overall heat transfer coefficient for the counterflow heat exchanger is 10.14 kilojoules per kilogram per square meter Kelvin. Continuing the calculation for the counterflow heat exchanger values, now we are going to calculate the heat gain of water using the formula Q is equal to mCp delta T, where delta T is equal to the difference of the temperature of the inlet steam and the temperature of the outlet steam. The calculated value for the heat gain of water is equal to 154.7436 kilojoules per kilogram as calculated in the slide. Then lastly, we are going to solve for the water's heat transfer coefficient during the process, which is equal to the heat gain of the water over the area using the inside diameter times the log mean temperature difference. And the calculated coefficient as shown in the slide is equal to 24.218 kilojoules per kilogram. Now is the presentation of the results of the countercurrent flow heat exchanger values. The heat exchanger values are shown in the table in the slide. So as you can see, the heat transferred by the steam is equal to 76.005 kilojoules per kilogram. The heat transferred by the water is equal to 154.744 kilojoules per kilogram. And the outlet overall heat transfer coefficient is equal to 10.14 kilojoules per kilogram per square meter Kelvin. And the inlet overall heat transfer coefficient is equal to 24.218 kilojoules per kilogram square meter Kelvin. The values for the parallel flow heat exchanger are to be calculated, which is in our sheet work for later. So now is the sample problem number 1 of heat exchangers, which tackles a parallel flow heat exchanger. So the problem is, a double pipe parallel flow heat exchanger is used to heat cold tap water with hot water. Hot water with a specific heat of 4.25 kilojoules per kilogram degrees Celsius enters the tube at 85 degrees Celsius at a rate of 1.4 kilogram per second and leaves at 50 degrees Celsius. The heat exchanger is not well insulated, and it is estimated that 3% of the heat given up by the hot fluid is lost from the heat exchanger. If the overall heat transfer coefficient and the surface area of the heat exchanger are 1,150 watts per square meter degrees Celsius and 4 square meter respectively. Determine the rate of heat transfer to the cold water and the log mean temperature difference for this heat exchanger. So we're going to use Polios method in solving the problem. So first, the given of the problem. The given of the problem are the following. So the coefficient of heat transfer of hot water is 1.15 kilowatts per square meter. the specific heat of hot water is given to be 4.25 kilojoules per kilogram degrees Celsius. The mass of hot water entering is 1.4 kilograms per second. So 3% of the heat given up by the hot fluid is lost from the heat exchanger. The surface area of the heat exchanger is 4 square meter, and the temperature of hot water is equal to 85 degrees Celsius, and the temperature of cold water is equal to 50 degrees Celsius. So required, the rate of heat transfer to the cold water and the log mean temperature difference. So next is the solutions. So first, we are going to solve the rate of heat given up by the hot water. The solution we are going to use is the Q equals mCp delta T, where delta T is equals to temperature in minus temperature out of the hot water, which is equal to 1.4 kilogram per second times 4.25 kilojoules per kilogram degrees Celsius times 85 minus 50 degrees Celsius. So the rate of heat given up by the hot water is equal to 208.3 kilowatts or kilojoules per second. So next is solving for the rate of heat picked up by the cold water. The problem stated that 3% of the heat is lost by the hot water due to the heat exchanger being poorly insulated. So the equation of the heat of cold water is equal to 1 minus 0.03 times the heat given up by the hot water, which is equal to 208.3 kilowatts. So by multiplying, we're going to get 202 kilowatts. Then lastly, we're going to solve for the log mean temperature difference. So the log mean temperature difference is equal to the rate of heat picked up by the cold water all over the coefficient of heat transfer of hot water times the area, which is equal to 202 kilowatts over 1.15 kilowatts per square meter times 4 square meter, and we are going to get 43.9 degrees Celsius, which is the log mean temperature difference. So the answer to the problem is the rate of the heat transfer to the cold water is 202 kilowatts, and the log mean temperature difference is 43.9 degrees Celsius.
Okay. Now for problem 2, I am Lydia Barquez, and let's talk about a counterflow double pipe heat exchanger. Now as you can see, we have here a sample problem that says a counterflow double pipe heat exchanger with an area of 9 meters squared is used for cooling a liquid stream. It has a specific heat of 3.15 kilojoules per kilograms per degree Kelvin at the rate of 10 kilograms per second with an inlet temperature of 90 degrees Celsius. Now, the coolant, which has a specific heat of 4.2 kilojoules per kilograms per degree Kelvin, enters the heat exchanger at a rate of 8 kilograms per second with an inlet temperature of 10 degrees Celsius. Now, the plant data gave the following equation for the overall heat transfer coefficient in watts per meter squared per degree Kelvin. Okay, our task here is to calculate the rate of heat transfer and the outlet stream temperatures for this unit. Now remember, we are given here counterflow double pipe heat exchanger that is used for cooling a liquid stream by a coolant. The rate of heat transfer and the outlet temperatures for both fluids are to be determined. Now, how do we do that? How do we solve this problem? So initially, we have to assume. Let's assume that steady operating conditions exist. The heat exchanger is well insulated so that heat loss to the surroundings is negligible, and thus heat transfer from the hot fluid is equal to the heat transfer to the cold fluid. We can also assume that changes in the kinetic and potential energies of the fluid streams are negligible, as well as the fluid properties being constant and there is no fouling. Okay, given properties, we have specific heats of hot and cold fluids, which are at 3.15 and 4.2 kilojoules per kilograms per degrees Kelvin, respectively. Now, to actually solve this, we are also given with the overall heat transfer coefficient equation. Manipulating the equation using the specific heats of the hot and cold fluids given in the problem, we can get an overall heat transfer coefficient of 1185 watts per meter squared per degrees Kelvin. Okay, now the rate of heat transfer may then be expressed as Q equals to mc delta T. This is a very common equation that we have encountered since we were in first years. Now, by manipulating the formula or by substituting the values into the formula, we can then get the rate of heat loss by the liquid stream at Q equals to 31,500 multiplied by the quantity of 90 minus the hot fluid temperature of the outlet stream. Similarly, we can also get the rate of heat gained by the Coulomb, which will be at Q equals to 33,600 multiplied by the quantity of the cold fluid temperature in the outlet stream minus 10. So it will be given by equation 1 and equation 2 respectively. So again, the rate of heat transfer may also be expressed using the logarithmic mean temperature difference, and it will be given by Q equals to the overall heat transfer coefficient multiplied by the area multiplied by the logarithmic mean temperature difference. Now, by using the equation 1 and equation 2, which I mentioned earlier, to substitute to the values of the cold fluid temperature and the hot fluid temperature of the outlet stream, we can then get the Q at 6.42 times 10 raised to the power of 5 watts. And using equation 1, we can then get the hot fluid temperature of the outlet stream, which will be at 69.62 degrees Celsius. And by using equation 2, we can then get the cold fluid temperature of the outlet stream at 29.1 degrees Celsius. So the final answer is summarized right here. So that's basically how to solve a simple sample problem regarding the counterflow double pipe heat exchanger. Okay, now that sums up all the sample problems, the experimental data, and the calculations regarding the parallel flow and the counterflow double pipe heat exchanger. Now is the time for the conclusion. Now again, the heat transfer coefficient is a quantitative measure of the convective heat transfer between a fluid medium and a surface. The heat transfer coefficient of a countercurrent flow is greater or higher than that of the parallel flow for both the inner and the outer tube. The temperature of the cold stream outlet of the parallel flow is always lesser than the temperature of the hot stream outlet, while in the countercurrent flow, the temperature of the cold stream outlet can exceed than that of the temperature of the hot stream outlet. Now we can conclude from this fact that the parallel flow is always restricted by the temperature of the cold stream outlet, while the countercurrent flow is restricted by the temperature of the cold stream inlet. Okay, initially, the only aim of this experiment given in our manuals was to determine only the overall heat transfer coefficient using steam to water and forced convection. However, during the course of this presentation, we have extensively applied the concepts we have learned in our momentum transfer in a laboratory setup, and we have enabled a visualization of the theory on a double pipe heat exchanger, as well as to calculate and obtain values of the log mean temperature difference, its effectiveness, and most importantly, we have been able to apply the concepts we have learned in the given practice problems to further our understanding on the topic. Again, to recap, in the case of a double pipe heat exchanger, of steam getting condensed on one side and water getting heated on the other side, the temperature of steam at condensation is 100 degrees Celsius, so the log mean temperature difference does not change, and hence the heat transfer in both counter and co-current, or also known as parallel flow heat exchanger, is the same. Parallel flow again is also called co-current flow. Don't be confused. Now, to recap what we have presented to you, the most common arrangements for flow paths within a heat exchanger are counterflow and parallel flow. Again, a counterflow heat exchanger is one in which the direction of the flow of one of the working fluids is opposite to the direction to the flow of the other fluid. Whereas in parallel flow exchanger, both fluids in the heat exchanger flow in the same direction. Under comparable conditions, more heat is transferred in a counterflow arrangement than a parallel flow heat exchanger, because generally the temperature distribution in the fluids are different. This in turn influences the heat transfer coefficient. Despite the possible identical temperature differences, the heat transfer coefficient is therefore also dependent on the direction of the heat flow. The higher the heat transfer coefficient, the higher the heat transfer due to convection. Heat transfer by convection is directly proportional to the heat transfer area and the temperature difference which exists between the bodies exchanging heat. While talking about temperature profiles of the two heat exchangers, this will only indicate two major disadvantages in the parallel flow design. First, the large temperature difference at the ends causes large thermal stresses, and the opposing expansion and contraction of the construction materials due to diverse fluid temperatures can lead to eventual material failure. The second is that the temperature of the cold fluid exiting the heat exchanger never exceeds the lowest temperature of the hot fluid. This relationship is a distinct disadvantage if the design purpose is to raise the temperature of the cold fluid. Now, the design of the parallel flow heat exchanger is only advantageous when two fluids are required to be brought nearly to the same temperature. Whereas the counterflow heat exchanger, it has three significant advantages over the parallel flow design. First, the more uniform temperature difference between the two fluids minimizes the thermal stresses throughout the exchanger. Second, the outer temperature of the cold fluid can approach the highest temperature of the hot fluid, or the inlet temperature. Third, the more uniform temperature differences produce a more uniform rate of heat transfer throughout the heat exchanger. Now remember, whether parallel or counterflow, heat transfer within the heat exchanger involves both conduction and convection. One fluid, or the hot fluid, convectively transfers heat to the tube wall, where conduction takes place across the tube to the opposite wall. The heat is then convectively transferred to the second fluid because this process takes place over the entire length of the exchanger. The temperature of the fluids as they flow through the exchanger is not generally constant but varies over the entire length. The rate of heat transfer varies along the length of the exchanger tubes because its value depends upon the temperature differences between the hot and the cold fluids. To simplify the things I have said, the counter current flow heat exchanger has its log mean temperature difference value greater than that of a parallel flow heat exchanger, and therefore for achieving the same degree of heat, the heat transfer area requirements are less in the case of a counterflow heat exchanger. This area saving is the biggest advantage of the counterflow heat exchanger over the co-current or the parallel flow heat exchanger. Now, as far as the advantages of the parallel flow heat exchanger are concerned, the parallel flow in heat exchangers minimizes the chance of freezing or channeling. Overall, the counterflow heat exchangers are more efficient than that of the parallel exchangers, and it is all because of a uniform temperature difference between the fluids over the whole exchanger and the fluid paths. Now that ends our presentation about the heat transfer in a double pipe exchanger. Since we have failed to find a video of this experiment from the previous years, flashed on your screens is the heat exchanger of Cebu Institute of Technology University. We are Group 1 and thank you very much.